Thank you. So, welcome again to lecture 2 of the preschool. Now, we're going to follow up from last time, and we're just going to, generalize what we did last class to tensors, introduce ourselves to tensors and how they transform and so on. And then we're going to do some brush over of special relativity, just some basic concepts that, just to review what you've already done, because we expect that you've already done special relativity before. So we're not going to go into deep details, but just stuff that you might require to sort of refresh in your memory of what you've done before. Okay, so following from last class, I would like to add a few things that I probably missed. So, for example, the fact that covectors in general take the form. So, remember that I defined covectors with the notation df, and it takes the form df equals to del f del x mu dx mu. Okay. Now, of course, we can verify this. And to verify, let's act it upon a particular vector, okay, v. So in this case, if I use this definition and I expand df, I should get del f by del x mu dx mu, and also expanding the vector into its components and using the coordinate basis, if you remember from last class, we would get something like this, right? So in this case, I can take the component v nu out. So in that case, I would have something like this, del f del x mu dx mu acting upon del nu. So you remember what del nu was? It was essentially a partial derivative over x nu, right? So in that case, I can have this to amount to the Kronecker delta, only giving 1 when mu and nu are equal, and 0 if mu and nu are not equal, right? So in that case, I would get v nu delta f delta x mu Kronecker. And of course, asserting the fact that mu and nu are equal, in that case, I would get v mu del mu f, which is essentially v acting on f, right? And essentially what you get out of here is the following.
I think there is a hearing issue from your end. Can you increase the volume?
Volume of my voice.
No, I think your device.
How do you increase the volume of the device when I am the one who's giving the input?
Is it better now?
Can you hear me? Maybe I can speak a little louder if that's okay. Can you hear me now?
Sure.
So the problem is I have a very bad cold, so my voice is a little not very up to the mark. So if you can't hear me, then maybe I can speak louder and more clearly. Can you hear me now?
Yeah, sounds better.
Okay, so people who maybe if you can't hear me, maybe increase your volume on your end, because okay. Yeah, but like I said, I have a very bad cold, so I don't know if I can do that for the whole lecture, but I'll try. Anyway, so like I was saying, that this definition was exactly how we define the covectors. Remember from last class, and I have it over here. I can probably show you here. Okay. So therefore, this is verified that you can write the covector in this particular form. So that basically means that the components of the covector, which is df over here, basically just are the gradient of the function f with respect to the coordinates x mu, because you have a certain partial derivative of f, which should give you the gradient of the function f, right? Now, we want to check what happens when we have a particular coordinate transformation. So let's consider coordinate transformation meaning that I take some coordinate x mu to another coordinate system, let's say x mu prime. Now, the basis covectors will transform as the following, which is a very common, known result, right? Because whenever we have a particular coordinate change, the basis or the basically underlying coordinates actually change via the Jacobian, right? Where this part over here is just the Jacobian, which essentially tells you how the new coordinate system is related to the old coordinate system, right? Via the partial derivative. So essentially, when you have a transformation as such, the basis covectors will just transform via the Jacobian as follows. Now, we know that the vectors are, coordinate invariant, right? Meaning that they should be basis independent, meaning they should be generalized to any basis that we choose, if you remember, right? Because last class, I defined the basis as follows, right? These were the covariant basis vectors. So in this case, we we sort of considered them as generalized, meaning that the basis vectors can be anything and still the vector definitions and covector definitions would still hold. So that makes these covectors and vectors basis independent, which means that under a coordinate transformation, they should still hold, right? They should still be invariant. So if I have a coordinate transformation of the basis covectors as such, then if I have the covectors, which remember was defined as omega, and in its components we wrote them as the following, right? So in order for these covectors to be invariant, they also must transform in a similar way, right? So the components, therefore, of these covectors should also transform via the Jacobian, or in fact the inverse Jacobian, if you can notice over here, or maybe you don't see the prime, but there's a prime over here and there's a prime over here, so therefore it must be the inverse Jacobian omega mu. So what this does is, if the component of the covector transforms in the following way, when you plug this in over here and you want to find omega prime, it would still always be equal to omega because of this transformation rule. Okay, and that is what we expect. We expect that the omegas, basically the covectors, should be invariant under coordinate transformation. Okay, and in fact, this is this transformation rule is one of the defining properties of covectors. Okay, so from our definitions of vectors and covectors and etc., we can now generalize this straightforwardly towards tensors. And remember that for the case of vectors and covectors, they were just linear maps, right? However, for tensors, it now generalizes to a multilinear map. So what I mean by that is, if you have a tensor which is of some rank mn, this would be a multilinear map which looks in the following way. So T, I'm denoting as the tensor T, which is a map from the contravariant or dual space of the tangent space in the following way, and also the tangent space itself. Maybe you don't understand what I'm writing now, but it will be clearer in a minute when I'm done. To R. Okay, so why do I have components of the dual space, the dual tangent space, and also the tangent space itself? Okay, because remember that I'm talking about a tensor of rank m and n, right? So in other words, what it means is that if I have m number of covectors and n number of vectors, a tensor of type m and n, which looks like this, just produces a real number because it maps to the real number space. Okay, are there any questions? Oh, a sharp corner, because sharp corners are basically corner points, right? Corner points are non-differentiable. You cannot define differentiability on corner points, right? Oh, so before I started tensors, I was basically talking about the invariance of the covectors, right? Because they are basis independent. If you remember, we can generalize them for any basis. That means that we can generalize them for any coordinate system. So that means that under a coordinate transformation, these covectors should remain invariant. So if these covectors remain invariant, that means their components should also transform in the same way, in fact, in the inverse Jacobian perspective, as the covectors or the basis covectors change. So in that case, when you write the covector in this following way, you would still get omega prime equals to omega, leaving it invariant. That is what I was talking about. Okay, so coming back to tensors, in other words, what it means is that if you have m of these and n of these, and you see that this is a map from the dual tangent space, so that must mean that I have m covectors, because covectors reside in the dual tangent space. And this is a map from the tangent space, so therefore this must be for n vectors, right? We would get a tensor of type m and n, and it would produce a real number, because the mapping is on the real number space. So the real number you can write as something like this, that goes up to m, and v goes up to n. So remember these notations from last class. We wrote the covectors with omegas and the vectors with v, right? So that means a tensor can heuristically have all components of a covector and all components of a vector, right? So now a little bit of recap from last class. If you remember that when we had a vector, we wrote the vectors as such, right, with the coordinate basis, of course. And when we had a covector, we wrote them as such, right? So that means that the vector components are denoted with the indices upstairs, right, as you can see from here. And the covector components are denoted with indices downstairs. So it means if a tensor of rank m and n are inclusive of both of these covectors and vectors, that means if I want to write tensor components, they could possibly and potentially have both indices upstairs and downstairs, right? And that is essentially why when we have a map of the tensor, we have both from the dual tangent space, as you can see from here, and from the tangent space, as you can see from here. So basically contribution from both indices, upstairs and downstairs. Okay. In fact, you can call vectors in general as tensors as well, just by incorporating their rank. So for example, this tensor component over here would be a 1-1 tensor, because it has one upstairs index and one downstairs index. Okay. Now a vector component, if I write it like this, right, it only has one index upstairs, right? So therefore this can be denoted as a 1-0 tensor, because I don't have any index downstairs. So the one that is denoting the downstairs indices is 0. Okay. Similarly, a covector component can be written as a 0-1 tensor, and so on. So similarly, if you have T mu nu, this is a 0-2 rank. If you have T mu nu like this with both of the indices upstairs, then this is a 2-0, and so on. Of course, you can have more indices as such, right? This would be a 3-0, and so on. Okay. Now, generalizing this further, if I have, let's say, E mu, right? Remember that this is a basis for the tangent space of the manifold. And of course, its dual basis was the indices upstairs, right? Then you can write the components of the tensor of T as mu1 going up to M, mu1 going up to, let's write this as N, and it would just be components of the basis vectors going up to M and the basis vectors going up to N in the following way, right? So of course you see that the indices actually determine the basis and the dual basis respectively. Okay, are there any questions so far? Yes. So the upper indices are actually, sorry, the upper indices are the basis for the covectors, right? And the lower indices are the basis for vectors, as you can see from here. Yes. Upper indices are for vectors. Sorry, upper indices are for covectors, as you can see from here, and lower indices are for vectors. Because if you have del mu as such, this just means that this is del mu by del x mu upstairs, which essentially gives you a downstairs index, if you think about it, because I have an upstairs index which is in the denominator. Okay. Okay, so moving on, like both vectors and covectors, tensors are also basis independent, meaning that under a coordinate transformation, they would still be invariant, right? So that means if I define a particular tensor in a coordinate system, in any particular coordinate system, the tensor will still hold its attributes in a different coordinate system. So that means that under a coordinate transformation, you would expect the change or the changed tensor to have the same properties as the transformation in vectors and covectors, right? So in that case, they would be changed via the Jacobian again, but depending on the indices, right? So now remember that for the component of a covector from here, if you look at this one, right? So from here, I have a Jacobian for a covector component as to have the old coordinate system in the numerator and the old coordinate system in the denominator, right? As such, right? So of course, if I have v mu prime, which is a vector component, right? I would expect the inverse, right? So that means that depending on your indices, if they are upstairs or downstairs, the Jacobian actually flips, right? So in that case, if I were to now sort of formulate a transformation rule for tensors, which can have m indices upstairs and n indices downstairs, then depending on how many indices I have upstairs, I would have the Jacobians accordingly. And depending on how many indices I have downstairs, I would have the Jacobian accordingly, right? So for upstairs indices, I would have the primes upstairs, right? And this would go up to m. Okay. And for the downstairs indices, I would have the primes downstairs, right? So let me write this as nu1 prime, nu1 up to n. And this would be my transformation law. Okay. And this is pretty straightforward. And you would see, in fact, that this would be invariant under coordinate transformation in the same way as we have invariance for vectors and covectors. Okay. Now, for tensors particularly, we have two important operations that we can do. One is that if you have two tensors, let's say I have two tensors S and T, where let's say S is of rank PQ and T is of rank RS. So now remember what rank means, right? Rank just means that you have P indices, P number of indices upstairs, Q number of indices downstairs. Similarly, for T, we have R number of indices upstairs and S number of indices downstairs, right? That is what rank means. Okay, are there any questions? What about T mu nu and T subscript mu nu? Will both component of tensor contravariant covariant? I mean, if you have T mu nu, this is contravariant with both indices contravariant, right? And if you have T mu nu, you would have both indices to be covariant as follows, right? Why expect the inverse? So we expect the inverse because, like I said, we want the tensors or the vectors, not the components. Remember, the components and the tensors are different because you define the tensors using the components, T mu nu, whatever, and the basis. So basis can be whatever the basis is for the tensor. So that would depend on how you're defining the tensor, right? Now, these are the components. This is the tensor. Okay, remember this. So similarly, for vectors, this is the vector, and the ones with the indices are the components, right? So if you want V to be invariant under accordion transformation, you need to make sure that V mu transforms in a particular transformation rule. Okay, so if you have indices that are upstairs, the transformation rule via the Jacobian should be inverse of what you would have for something or some component that has indices downstairs. Okay, because of course the basis vectors would then also be determined, right? Because the basis vectors also follow the transformation rule via the Jacobian as such. Okay. Now, like I was saying, that for tensors, you can have two particular operations. If we consider first, let's say we have two tensors like I wrote over here, S and T, where S is of rank P and Q and T is of rank R and S, you can in fact construct a larger tensor. So you can construct a larger tensor with indices P plus R and Q plus S. So maybe write it like this. Okay, using an operation known as the tensor product. So what I mean by that is if you product these two tensors, which we write via this notation, where let's say, because you can have P and Q, right? Where for S, let's say P and Q, where P basically denotes the upstairs indices, if you remember. So then I would have covectors, right? And it would go up to P. But now, since I have the tensor product between S and T, my overall indices should be P plus R because I would add the upper indices, and Q plus S, adding the lower indices. So they should go up to P plus R. And for the contravariant ones, I would have V1 going up to Q plus S. Right? So this would just mean that I have a multiplication between S, which goes up to omega P, and for V components going up to Q times T going from P plus 1 to P plus R, so that overall the total indices that you have for upstairs is P plus R, and VQ up to VQ plus S. Okay, so this is your definition of the tensor product. Now, in terms of components, of course, this simply means that if you have the tensor product between S and T, where you have the components, like I said, going up to as follows. So let me write this as P and rho 1 to R. And for the downstairs ones, I would have up to Q, and this would be up to S, right? So this would just give you S having indices up to P. Q, I'm just incorporating what I wrote over here with the indices over here, okay, for you to not get confused. And then T would just go from rho up to R, and sigma to, so sorry, I should have written this as rho P plus 1 going up to rho P plus R, and sigma Q going up to sigma Q plus S. Okay. So this is the first operation that you can do for a tensor product. Now, the second operation that we can do is we can lower the rank, and you can create a lower rank R minus 1 and S minus 1 tensor by contraction. Okay, these are the two very important tensor operations. Now, in terms of components, what I mean by contraction is basically is defined as summing over one upper and one lower index. Okay, so if you want to see that, for example, you can write a tensor as such, right? And you can define it by basically having the same index upstairs and downstairs. So what I have over here is that I have a lambda upstairs and I have a lambda downstairs, right? So if I have the same index upstairs and downstairs, we call this summing over, okay? And when you sum over one of this, or basically two of these indices, upstairs and downstairs, they are contracted out. And what you're left with is just the indices that are left, okay? So mu, rho, and sigma, so which are the ones that are left over here, okay? Now this contraction is also denoted as Einstein's summation rule, which is just a notation to tell you that lambda over here, which is the repeated index, is summed over. Okay, that means there is a summation over here. So let's say if I have lambda to run from 0, 1, 2, 3, if I write T mu lambda rho sigma rho over here, where I clearly see that the indices are repeated upstairs and downstairs, that means that there is a summation, a hidden summation, where I can write a summation as such, where lambda goes from 0 to 3 in the following way, which would basically give you what? It would give you T mu 0 rho sigma 0 plus T mu 1 rho sigma 1 plus T mu 2 rho sigma 2, and finally T mu 3 rho sigma 3, and follows. Okay, so whenever we have a summation as such, which we call an Einstein's summation. Basically, the indices can be contracted out, and by contraction, you can lower the rank by the contracted index. Okay, so since we have one index over here that is contracted with the other index downstairs, that means you would lose one of the degree of freedom, right? And therefore you would have a lesser rank, one lesser rank tensor. Okay. Now, in the case of a 1-1 tensor, so for example, if I have a 1-1 tensor where the indices of the 1-1 tensor is summed over, meaning, let's say if I write a 1-1 tensor, and remember what 1-1 means is it means that I have one index upstairs and one index downstairs, and both of these indices are summed over, I would get T, which is called the trace of the tensor. Okay, and this is how the trace is defined. Now, remember that this T and this T over here, or in fact, this T over here is not the same. Okay, this T over here is basically the tensor that is basically an amalgamation of all the tensor components. Is basically an amalgamation of all the tensor components, is just the trace. Okay, so because it's more or less implied what we're talking about when we're doing the calculations. But remember that this trace does not have any indices, whereas the tensor T that we defined earlier is an amalgamation of all the tensor components. Okay, but here this is just the trace. Now, finally, if I have any arbitrary tensor T, so for any arbitrary tensor T, we can symmetrize or anti-symmetrize some of its indices. So for example, if I consider a 0-2 tensor T, now for that, if it has components T mu nu, sorry for my voice, but if I have components T mu nu, then we can define a symmetric tensor. So you can have a symmetric tensor, let's call that T. Oh no, I already used T. So let's call that S. And also an anti-symmetric tensor. Let's call that A, with components in the following way. So you can have S mu nu, which remember is the symmetric tensor. Maybe I should write the A over here because that looks like asymmetric, which is not true. So we have S as a symmetric tensor. So we can symmetrize the components, in fact, symmetrize the tensor T by writing it in this way, which can be defined in the following way with brackets. So this bracket basically means that mu and nu is symmetric. Okay, so it's symmetric, meaning that if you have T mu nu, it is equal to T nu mu. Okay, and similarly for the antisymmetric tensor, we can write it as T mu nu minus of, oh, I should have written mu nu over here. Sorry for my mistake, but over here I should have minus of mu nu, and this can be defined as mu nu but with a different bracket. So this bracket means anti-symmetric. And what anti-symmetric means is basically T mu nu is equal to minus of T nu mu. Okay. Now this can be generalized also to higher rank tensors. For example, if you have something like this, okay, and with this bracket I mean that I would have symmetry over mu nu, which I can write in the symmetric components as such as mu nu rho sigma plus T nu mu rho sigma as follows. Okay. Now, more or less, we can deal with tensors as such. And in fact, this is more or less what you would need if you are going to work with general relativity. Basically, these tensor components and tensor symmetries are aspects that we mainly use when we're doing GR. Okay. Are there any questions so far? Hidden summation means that basically I'm not writing the summation here, right? So basically it just implies that there is a summation. I'm not writing the summation notation, but it's just implied. So therefore I said hidden summation, because you're not really writing the summation notation, but the summation is there. Okay. Does writing the up or down indices to the left or right matter? What do you mean by left or right? You mean something like this? Something like this? Yes, it actually matters because, well, depends on how mu and nu run, right? So let's say mu runs as 0 to 2, nu runs as 0 to 3, or something like this, like 0, 1, 2, and 0, 1, 2, 3. So if I define a tensor component as such, that means that I would have components like 0, 0 plus 0, 1 plus, let's just have nu 0, 2, da 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 up to 0, 3, and so on, right? By permitting all the nus and mus. On the other hand, if I wrote something like this, then I would have components that may not be the same. So let's say 1, 0, right? Plus 2, 0, or something like this. So they're not really equal, right? Components can differ. So of course it matters. Okay. Um, are there other questions? Wait. What is the notation for the symmetry of two indices that are not together? What do you mean by not together? You mean if they're not side to side? Is that what you mean? Because if you're talking about if they're not side to side, basically that would depend on the tensor, right? Let's say, for example, if I'm considering something like this, right? But my symmetry is over mu and nu. But then I have to understand how my tensor behaves if I juggle between these two indices, right? So different types of tensors actually abide by different types of symmetries, which you will encounter when you do GR. Like for example, the Riemann tensor, right? The Riemann tensor has symmetries between all four of its indices, right? So in the way you move, let's say these two, you will have a different symmetry property uh, compared to when you move these two indices. So it actually matters on how you are defining the tensor. Okay, the symmetry properties can be different. Okay. How was omega prime equals to omega y covector specifically invariant under coordinate transformations? Okay, so covectors are invariant under coordinate transformations because remember when we defined last class, when we defined covectors or vectors in general, we did not really particularly define any sort of basis vectors, right? Basis vectors can be arbitrary. So in that case, if basis vectors are arbitrary, that means that in our definition, we can plug in any type of basis vectors and the definition would still hold. And basis vectors are essentially defined by the coordinate system that you're working in, right? So if the definition works for all basis vectors, then it should work for all coordinate systems, meaning that covectors and vectors are coordinate independent, right? Via a coordinate change, they would still hold the same attributes. Okay, that is why they're specifically invariant under coordinate transformations. While lambda equals to 0 to 3, Where did I write lambda equals to 0 to 3? Oh, over here. Oh, because I just gave you a specific example. In general, we do live in a 3+1 universe, right? Basically, you have one temporal time index and three spatial. So I just gave you a particular example as such. And in fact, in GR, you will see that all indices go from 0 to 3 because 0 stands for time and 1 to 3 stands for all the other space, three-dimensional space. Okay. How do we obtain a trace of tensor which have both indices downstairs instead of one up and oh, we can't really do that. Let's say if you're talking about something like this, right? You won't be able to find a trace directly, but you can find a trace if you find a mechanism which actually lowers the indices downstairs and makes this index exactly mu, right? Because for me to get a trace, I need to have the tensor component look like this. So if I can find a mechanism which not only lowers mu but also makes it into mu, then I can have a trace, right? And I think this is something that Nabil Bhai will cover because he's going to talk about the metric tensor, and you will see further that we can use the metric tensor to do exactly this. So you can lower indices and change the indices depending on what index you're using in the metric tensor. Okay. So you can only find the trace if you have a mechanism as such where you use the metric tensor to lower or raise indices. Okay, is there some significance to adjacency of some indices that is expressed physically in some manner? Yes, like I said, that it depends on how you are defining the tensor, right? Some tensors have symmetry properties that are different from other tensors. So depending on how you place your indices in the tensors, they can have different symmetry properties. Like I said, for the Riemann tensor particularly, which is one of the more important tensors that you will see in GR, they have symmetry properties in how you move about with the indices. No. Well, Um, yes and no. Well, basically, if we lower the index, it would be a different object because, like I said, you would need the metric tensor to lower the indices, right? So that means that you are multiplying the metric tensor with, well, you're multiplying the metric tensor component with the tensor. So basically, what you have at the end is a multiplication of these two tensors. So obviously, it would be a different object, but heuristically, these are at the end of the day tensors. So not really a different object, but maybe a different mapping, if you want to think of it like that. Okay. What if tensor would be antisymmetric? Then we can say that its trace is 0. Yes, because well, that would depend on how many indices there are, right? Like for example, the trace would be 0 if you have equal amounts of negative contributions and positive contributions, right? So depending on how you have mu and nu or the indices to run from, you can say that the trace is 0. Yes. Okay, so I'll move on, maybe answer the questions a little bit later on. Now, so we're done with the differential geometry part. And now what we're going to do is we're going to move on to review some elements of special relativity. Okay, so special relativity is pretty simple, but very profound. In fact, in the way we view the universe, relativity actually, places our understanding in a very special light, right? So it is simple, but like I said, it's very profound, and it is based on a very articulate idea, which is that the speed of light is the same in all inertial reference frames, right? So one of the very important postulates of special relativity is that the speed of light is the same in all inertial reference frames. And of course, if it is indeed same in all inertial reference frames, it does not depend on the motion of the observer. Right? So, in fact, from this idea, Einstein deduced some far reaching consequences about the nature of space and time. Now, one of the fundamental things in special relativity is Lorentz transformations. And the reason why this is fundamental is because to fulfill this particular postulate, where we have the speed of light to be the same in all inertial reference frames, we need these coordinates, which we are using to, let's say, describe a particular space, to be Lorentz invariant. Okay, that means that we have to have them abide by this Lorentz transformation. Okay, what I mean by that is, let's say we consider two inertial frames. Let's call them S and S prime. And from the point of view of S, so from S, the frame S prime is moving with a velocity let's say v, which is in the x direction. Okay, so in that case, the coordinates in S prime would be related to the coordinates in S via the Lorentz transformation, which is given as t prime equals to gamma t minus vx by c squared. X prime would be related to x and t via this relationship, and similarly for y prime would be y, because the only boost that I have, or the velocity that I have over here, is in the x direction. So the x components will change, leaving the other spatial directions the same. Okay, so this transformation is called the Lorentz transformation, which I'm pretty sure you've already seen before. And this transformation actually confirms that the speed of light is the same in both frames. Now, if you're not familiar with this, gamma over here is called the Lorentz factor, and it is defined as 1 by 1 minus v squared by c squared. Okay, so this Lorentz transformation actually is what confirms that the speed of light is the same in both frames. Now, how do you verify that? Now, consider that you have light, and light is traveling in the x direction. So in that case, the light ray would obey x equals to ct, right? Now, what we can do is we can plug this in over here in the transformation equations, right? And see what it would be in S prime. So if in S you have x to equal to ct, then in S prime, using the transformation coordinates, or basically the transformed coordinates, you can find x prime, which would basically be equal to gamma over here as x minus vt, where x is equal to ct, if you remember, right? So in that case, I would get gamma times ct minus vx by c, right? Also plugging in t from there. And this would equal to ct prime, which you can find from here. So hence what I would have is they would be scaling in the same way. So x prime equals to ct prime, and x equals to ct is the same. Okay. Now, another thing that you can note from here is that from the Lorentz transformation equations, you can see that time and space have been mixed, right? Because over here I'm denoting t prime as with both t and x components, and x prime with both x and t components. So the reason why you can actually do this, because you can sort of think about this from an analog of spatial rotations, right? Because in fact, in spatial rotations, you have the mixing of terms like this, like you have different dimensional terms to mix together. So to understand that further, maybe consider three-dimensional Euclidean space. So let's say in 3D flat space, which is also called Euclidean, if you have this space to have coordinates, let's say x bar to be xyz, okay, in 3 dimensions, and this is defined in some frame, let's say S, and let's say you have a second frame S prime. Sorry for my voice, but if you give me 2 seconds, I'll just, have a drink of water and come back. Okay. So, like I was saying, if you have now another frame, let's say S prime, and for that frame, we have coordinates denoted with X prime, which is given as, let's say, X prime, Y prime, and Z prime. And this is in a frame S prime. Now, you can relate both X and X prime, and let's say there has been a rotation between S and S prime. Okay. In that case, you can relate X with X prime, or let's write it as X prime equals to X via a rotation matrix, right? And this rotation matrix is basically what will mix mix the components, right? X, Y, Z, and so on. So from here, the two coordinate systems will definitely share the same origin, because try to think of it like this. Let's say you have three. Okay, maybe it'll be easier if I can visualize it in 2D. What I'm talking about. So let's say you have coordinate axes as such, right? Let's say this is S, and you have X prime and Y prime over here. And we can clearly see that X and X prime are actually related via some rotation, right? However, they still share the same origin, but are just rotated with respect to each other. So therefore, if you were to write the coordinates for S prime, they would have become a mixture, right? Because you can see X prime now exists in the XY plane of S. And therefore, if you want to write some equation for X prime, it would require both X and Y to define X prime. So therefore, there would be a mixture of both X and Y, right? So similarly, Lorentz transformations can be thought of as rotations between time and space, okay, which is an interesting observation because it has profound implications. So this particular idea, basically mixing space and time via Lorentz transformations, give you three particular implications. Number one, events that are simultaneous in one frame are not simultaneous in another frame. Number two, this also gives rise to the fact that moving clocks run slow, which is also called time dilation, which is an implication of special relativity. And thirdly, you have moving rods are shortened, which is also called length contraction. So these are the three implications that special relativity gives you because of this particular thing. mixing space and time via Lorentz transformations. Okay. Okay, so questions. I'm facing a problem which is very basic. Why we take speed of light constant? Oh, because I mean, you would need something to be invariant under the postulates that you have, right? Number one. Number two is that is how nature works. We do have speed of light to be constant. I mean, that is what we observe. So that must be true, right? So whenever you postulate a theory as such, you need to make sure that you're incorporating reality, you're incorporating what nature actually allows you to. So in that case, of course, if we see that in nature speed of light is constant, we need to build our theory around it, right? So of course, speed of light has to be constant, number one. Number two, can we derive STR from only first principle? What is STR? Special theory of relativity. And what do you mean by first principle? That speed of light is constant? I mean, yes, that is what we're doing here. Hmm. Yes, and that is what we're doing over here, right? Now, could you please elaborate what you've said from Lorentz transformation? We can see that space-time are mixed. Okay, so from here, you see that the transformation coordinates, T prime, which is the transformed coordinate, the Lorentz transformed coordinate T prime, has both indices T, okay, maybe I should not say indices, has both terms T and X, right? Where T temporal part, temporal direction, and X is a spatial direction, right? And for X prime also, you see that it is defined via the transformation with X and T. So normally you would think that the transformations should happen in the direction that uh, it was originally in, right? I mean, whenever I think about transformation, let's say, for example, X is being transformed, right? I would normally think that X, if boosted, should have a transformation in the X direction. However, through Lorentz transformation, I see that if I change or transform X to X prime, I not only need X, but I also need T. That means for my transformation, I'm sort of basically mixing the components, mixing T and X, right? So that only happens if you have a rotation, okay? And via that, you can sort of fix an analog to rotation in this way, and you can think of it as mixing space and time when you have a Lorentz transformation. So this particular idea actually gives rise to these three implications of special relativity, which I think you can find elaborate explanations of if you open a book on special relativity. But like I said, I cannot obviously, put time on running a course on special relativity. So I'm just brushing over what we know, which are fundamental to our understanding. Okay. Okay. So the next important thing to define in special relativity is, of course, the space-time. And how do we incorporate four vectors in the space-time? Okay. So space-time and four vectors. Okay. So, so although we understand that you can have an analog of rotation, right? And we know that rotation would change components of vectors. So what I mean by that is that, let's say, if you have some delta x, right, which essentially maps the difference between 2 points, right, and this is a vector that connects 2 points in space, right? So let's say delta x is some x2 minus x1, okay, where this is basically a vector that connects x2 and x1. So if I have a rotation between x2 and x1, I know that this delta x would differ, obviously, right? However, rotations will not, or maybe I should write the whole thing. Rotations will not change distances. And what I mean by that is that, okay, so think of it again from the rotation perspective. Okay, maybe I can use the figure that I have over here. So let's say I have some point over here that is being rotated somewhere over here. And let's say I have another point over here, which is also being rotated over here. Okay. So now, of course, this vector, in the way that it is connected via these 2 points, will differ when I transform it via rotation. You can see, obviously, it changes direction, right? So, of course, it will change. However, since the rotation is as such, the distance, the length, and the actual scalar lengths that exist between these 2 points will still remain the same in even after whatever rotation I make, right? So in that case, what I can write is the magnitude between these 2 points, basically the vector that connects these 2 points, the magnitude, meaning the scalar length between it, will remain invariant under Lorentz transformation, which is basically our analog of rotations, right? So in that case, although we think time and space are relative, all observers will actually agree on the space-time interval, which is basically your length, scalar length. Okay. And the way you can think about this is if I can write the scalar length as follows, right? For 3 dimensions, if I incorporate this into a space-time, right? I can write this as delta S squared as minus delta t squared plus delta x squared plus delta y squared plus delta z squared. Okay, and this is actually called the space-time interval. Okay, now we can demonstrate this explicitly for the specific transformation, which is the Lorentz transformation, and we can do this for the x direction. So let's just consider the x direction. So in that case, you can see that when we have a Lorentz transformation, this interval actually stays constant, as in it does not change. Okay, so let's say I have delta s squared. Okay, and let me put the transformed coordinates delta t prime squared plus delta x prime squared. In that case, if you remember the Lorentz transformation equations from here, these are the ones that I'm using. And I will put this over here. So therefore, I will have the factors of gamma, right? And I will have c delta t minus v delta x by c squared plus gamma squared delta x minus v delta t squared. This would equal to minus gamma squared c squared minus v squared delta t whole squared plus gamma squared 1 minus v squared by c squared delta x whole squared, right? Now, this is just, inverse of gamma squared, right? This part. So therefore, they go away because they give you 1. And for this part, I will have just c squared left. And for that, you will have finally minus c squared delta t squared plus delta x squared, which is exactly what we started with, right? From here. So remember, we're just doing it for x, so therefore I ignored these two. But you can also show that if you have a transformation for both y and z as well, you will still come down to an invariant delta s squared. Okay, so that is a big result. It means that the interval or the spacetime interval over here is invariant under Lorentz transformation. And whatever is invariant under a Lorentz transformation, we call them Lorentz scalars. Okay. Now, this is special relativity, but in general relativity, we will consider spacetime intervals that are between points which are very infinitesimally close to each other. So, of course, if they are infinitesimally close to each other, we transform the deltas to differentials, right? ds. So in that case, the spacetime interval will basically look like this, where all the deltas will now just be transformed differentials as follows, and this is called the line element. Okay. Now, note that ds squared over here or delta s squared over here is not essentially positive definite, right? Because you have a minus over here. So depending on how dt squared is, or how they are scaled accordingly, we don't really know if this is positive definite, right? So this idea actually plays a very important role in our understanding of special relativity, because let's say if two events are time-like separated, so if two events are time-like separated, we will have delta s squared to be, sorry, negative, okay? And the reason why that is so is it would mean that they are closer in space than in time. Okay, so if they are closer in space, that means that dx would be smaller, or dx, dy, dz, as in the spatial parts, would be smaller than dt, right? Because dt, that would mean that 2 points have a very big difference between them in time, and hence dt, which basically maps this change, would be big. And if they're very close to each other spatially, that would mean that 2 points spatially are close to each other, and hence the change between them is small, and therefore dx, dy, dz would be small. And if dx, dy, dz is smaller than dt, then of course ds or delta s would have more contribution from the negative, and hence would be negative, right? So this is when we say that events are time-like separated. Okay. In contrast, if we have events that have delta s squared to be positive, they are said to be space-like separated. Okay. And finally, if we have del s squared to be equal to 0, we call them light-like separated. Okay. And basically, light-like separated means that these events can be connected by a light ray. Okay. Now, the set of all points that are light-like separated from a particular point basically define this particles or this point's light cone. Okay. So in special relativity, we have something called the light cone that looks like this, which is plotted against space and time. Okay. So T for time and S for space. Now, points that are time-like separated, which means that they abide by the first condition over here, they are inside the light cone. Okay. That means that, of course, like I said, that they are closer in space, right? So they don't really deviate much in the x-axis, but they deviate a lot in the y-axis, right? They are inside this light cone. Now, points that are space-like separated, which means that they are closer in time and farther away in space, they would deviate more in space than time, and therefore they would be outside the light cone. Okay? And the ones that are light-like separated, they would be exactly on the edge of the light cone where ds squared is equal to 0 or delta S squared is equal to 0. Okay. So now when we have causality, which means that we abide by the fact that, speed of light is constant and, we cannot travel faster than the speed of light. If we respect causality, then a particle must travel on a time-like path through space-time, meaning a particle must stay inside its light cone. Okay. And when it does, and if I have a particle that is moving along inside the light cone or inside its own light cone, we call this path the particle's world line. Okay, so this is basically the particle's world line. Now, this is how we basically map the whole of special relativity, in the sense that all of physics that we, do, and all of physics that we see and observe are inside the light cone of an observer. Okay. Yes, tachyons are space-like because tachyons travel faster than the speed of light. Okay. Okay, so moving on, since we understand that we have a very intimate connection between time and space in relativity, we can see that they're mixed and all of that stuff. It of course makes sense to combine them into a 4-vector, right? Which means that we can define coordinates as 4 vectors as such, where we would have both incorporation of time and space. So something like this. And the reason why we have C over here is so that, dimensionally the 4-vector is correct for both time and space. Because you understand that time and space don't really have the same dimensions, right? But if you want to incorporate them into one vector, that should, of course, abide by dimensional analysis, and it should have the same dimensions. And therefore, we have to incorporate C over here. Now, notice that I have not used natural units over here, so I have not yet, equated C to 1, okay, yet. Now, over here, this mu basically is a Greek index that, like I said, runs from 0, 1, 2, 3, where 0 is for time, 1, 2, 3 are for the rest of the 3-dimensional space. Okay. And in GR particularly, you will see that whenever you use Greek letters, they always incorporate time. So Greek letters actually mean they run from 0, 1, 2, 3. And if you use Latin letters, let's say I, J, K, whatever, Latin letters, they will run only for space. So 1, 2, 3. Okay, this is something that you will encounter when you do general relativity in general. Okay. Now, to make the symmetry between time and space more manifest, let's equate C equals to 1. And using natural units, you can actually basically see, or basically visualize the symmetry between time and space more accurately, because if I put C equals to 1, then they're all in the same footing, right? Now we can write the line element, which I wrote over here, ds squared, using tensorial representation, using the metric for special relativity, which is the following. So this is in tensorial representation. You can see that I have the indices now, right? Where eta mu nu over here is called the Minkowski metric, which is basically the metric for Euclidean space. Okay. And particularly eta mu nu takes this form in matrix representation. It's minus 1, 1, 1, 1, and all the other off-diagonal terms are 0. And remember that I'm using a signature where I'm considering minus for the temporal part, which is this one, and plus for the other spatial parts. And this is called mostly plus signature. Okay, so in general, for GR, I think we would use this signature most often, which is mostly plus. So we consider time to be in the negative footing and spatial indices or spatial components to be in the positive footing for matrices. Okay. Now we have the line element over here. Now let me write this down again here for reference, because I want to talk about this line element a little bit more. Now, the tensorial representation is as such, you can see that there are indices that are repeated upstairs and downstairs. Now, if you remember from before, I said that if we have repeated indices as such, where we have mu and nu to be um, repeated upstairs and downstairs, it means that there is a hidden summation, which is the Einstein summation. So that means that mu and nu, they actually run from 0, 1 to 3, and I can write them as a summation in the following way, right? And it will just give me what? Eta 0, 0, dx 0, dx 0, um, plus eta 1, 1, dx 1, dx 1, plus eta 2, 2, dx 2, dx 2, and finally 3, 3, dx 3, dx 3. Now, can you tell me why I've only taken 0, 0, 1, 1, 2, 2, and 3, 3, and not the other permutations? Because I can have permutations, right? Because mu and nu run from 0, 1 to 3. So I can have permutations as such. But can you tell me why I only used the indices that are equal to each other? Yes, exactly. So off diagonal terms are 0, right? So even if I use, let's say, 1, 0, or other permutations as 0, 2, or something like that, they would give me these components, which are either way 0. So that means they do not really contribute to the summation as much. So therefore, the only components or the only terms that contribute to the summation are the ones that are in the diagonal, and the diagonals have equal mu's and nu's, right? Sorry. Okay. So now moving on from here, we can also write the Lorentz transformation in tensorial form. So under Lorentz transformation, you would have the space-time 4 vector. So let me write that as x mu nu. Remember, the prime just denotes that it's been transformed by the Lorentz transformation. And we can write the Lorentz transformation matrix in the following way. Okay. So in tensorial form, this is basically your Lorentz transformed uh, 4 vector, right? And according to the equations that we had earlier, which is for this one, right? So that means that what you're basically doing is you're having some x prime, which is being Lorentz transformed. So that means that whatever you're multiplying over here to your x mu should give you the Lorentz transformation equation that we had earlier. So that must mean that we should have lambda mu nu to be a 4 into 4 matrix, obviously, because it runs from 0, 1 to 3, all of the indices. So therefore, this must be a 4 into 4. And for the specific Lorentz transformations, this must take the form of gamma minus gamma v minus gamma v gamma, and the rest are 0. And this is 1, and this is 1 for the y and z, because y prime equals to y and z prime equals to z, right, as we saw. So the only terms that are affected by the Lorentz transformations are these ones. And now remember, this is the 0th part, which stands for time, right? This is 1, 2, 3. So therefore, this is x, y, z. So therefore, the temporal parts and the x direction parts are only affected by the Lorentz transformation. And once you multiply this over 2x mu and if you multiply this with x nu, then you should get the transformed equations, as I wrote earlier. So now remember, x prime mu is just x0, x1, x2, x3, right? Because mu runs from 0, 1 to 3, so this is what I would get. And of course, with the primes. And x nu also runs from 0, 1 to 3, so this is what I would get. And you multiply this with this 4 into 4 matrix, and this should give you the system of equations that we had earlier. Okay. Now, in general, this ds squared, like I said, should be invariant under Lorentz transformation, right? And this invariance of the line element requires that you define the eta matrix, or basically the Minkowski metric, to transform in this way. Because if this transforms in this particular way, then it ensures that ds squared is invariant under Lorentz transformation. Okay, just plug it in. Like if you are confused how this happens, just plug in the transformed eta mu nu over here with the transformed dx mu, and you will see that ds squared is invariant under this Lorentz transformation. And particularly, in fact, the set of matrices that satisfy this particular constraint actually define the Lorentz group. Okay, so the set of matrices that satisfy this constraint define the Lorentz group. Okay. Now, of course, like I said, if you have definitions of x mu over here, right, you should also have their co-vector components as well, right? So if I have defined x mu's like this, they should have their dual as co-vector components x mu, like this, right? So the way you can define these covectors is actually use the Minkowski metric to raise or lower the index, right? Like I said earlier, remember that you can use the metric to lower or raise indices. So in this case, since for special relativity, the underlying metric is the Euclidean metric, which is the Minkowski metric. In that case, we will use the Minkowski metric to lower the index of x mu over here so that it gives us x mu, which is the covector or its dual. What I mean by that is essentially you can write x mu over here with the metric component and multiplying it with x nu, which is the vector component, and it should give you minus d x y z. Okay, so what I did over here is that you see that nu over here is contracted, right? And when it's contracted out. And the way you raise or lower indices, and I think Professor Nabil Iqbal will also expand on this a little bit further. The way you raise or lower index using the metric is if they're contracted out with one of the index of the metric, then what you have left is the surviving index. So over here, you see that the surviving index is a mu that is downstairs. So therefore, since I'm using the metric to lower nu over here, I should get the surviving index, which is a mu downstairs, which is exactly what I have over here. Okay, so therefore, you can relate the covector with the vector using the metric in this following way. And since you have eta mu nu, to have indices minus over here, you have components minus 1, 1, 1. So it should give you minus t x, y, z as follows. Okay, so here x mu, we call this a covariant component of a vector. And x, let's write mu with an upstairs index, is called a contravariant component of a vector. Okay, now of course I use the metric over here to lower the index, right? But I can also use the metric to raise the index. So let's say if I have x mu like this, and of course I will relate it with some x nu which is downstairs, which is basically the coordinate that I'm raising the index of. So in that case, I would need a metric that has the upstairs indices, right? So therefore, I would need its inverse. The metric that I used over here, I would need its inverse to raise this index. So here you see that nu again is contracted out. So therefore, I would get the surviving index left, and I should get x mu like this. Now, eta with upstairs index like this is actually the inverse of eta with downstairs index like this. And in fact, you can define their relationship, and you can write eta mu rho and eta rho nu with the Kronecker delta. It's similar to how we've defined, vectors with covariant and contravariant indices earlier, if you remember, right? Okay, so one of the more important covector, or an example of a covector as such, is del mu, which is again defined as del x mu, which has components del t, del x, del y, del z, if you're working in Cartesian coordinates as follows. Okay, so this just means that this would boil down to del by del t, del by del x, del by del y, and del by del z, respectively. Okay, and this is an important covector because it appears very frequently in relativistic equations of motion. I mean, of course, these are partial derivatives, right? So of course you would have them in equations of motion. Okay, are there any questions? Hmm, okay, how do we describe a phenomenon physically space-like separated from space-time diagram? Well, we don't deal with space-like separated phenomenons because, like I said, they break causality, which means that they would have to um, travel faster than the speed of light, right? How do you observe something that is moving faster than the speed of light? Any of our any observation, in fact, is determined by a particular limit, which is the speed of light, right? So a phenomenon that takes place outside this boundary would not be observed by us. So in this, at least at this level, you would not have a phenomenon that is space-like separated. Well, mostly negative is just a convention. So it's just a convention that people use. So in general, I think in QFT or in particle physics in general, you use mostly negative convention, where you have the metric to assign negative values to the spatial components and positive values to the temporal components. However, in GR and in cosmology, you use mostly plus. So you have the temporal components to have minus and the rest to have plus. Oh, I think somebody already answered this question. Okay, dx mu basis for one form, so just notation confusion. No, dx mu is not, well, okay, so there's the difference between one forms over here. You see that I did not really write a tensor product over here, right? So these are not one forms, these are just differentials. I could have written dA squared as, well, something like this. And in that case, I would have used one forms. So if I wrote it like this, these would be one forms. But I just used, and actually I just dealt with the components only. So here, these are not one forms. These are in fact just differentials. So this, I know this notation might be a little confusing, but over here, these are not one forms. But you can, of course, define the line element. In fact, the metric, since they are all tensors, you can define them with one forms as well. Okay, but here I'm just dealing with components. So these are not tensors, but they're tensor components. Therefore, these are just differentials. Okay. Off diagonal metric terms are zero. Okay, I think I read that already. Does the trace of the Minkowski metric signify anything? Um, well, not really in this particular case. But if you were to, let's say, deal with the trace, you just have, something that looks like this. It doesn't really, have any importance as of now. Okay. Um, okay. Why is there negative? What is negative? Which one is negative? Maybe I should have read that when I was doing the lecture, but sorry, I wasn't paying attention to the chat. Okay. So I think one of the questions have been answered. Physicists deal with space-like separated events. Well, that depends on the type of field that you're working on. There are many particle physics notions where you do deal with space-like separated events, I think, but I'm not really familiar with that line of work. So I'm not sure if there is a particular field of physics where they deal with space-like separated events. But of course, theoretically, they're important because they let us differentiate between what is a time-like event and what is a space-like event, right? And any equations of motion that you define in a space-like event would be null for, for mechanical reasons, of course. Yes, of course, the placement of the index of mu nu, of course, matters. Like I said earlier, that depending on how mu and nu run, the placement will differ, right? So of course, remember that these are defined by matrices. So your mu and nu basically assign the number of rows and columns. So if you interchange them, they would just mean that you're interchanging rows and columns, which would give you a different matrix. So hence, obviously, the placement matters. Okay. Okay. So moving on. I hope I answered all the questions. Should I move on, or do you guys need a break, like a 5-minute break or something? Okay, there's another question. There was negative sign for V terms in Lorentz transformation matrix. I've seen them as positive ones too. So why we are using different signs? I think what you're talking about is convention. So since I'm using a convention where I'm using mostly plus for spatial terms and mostly minus for temporal terms, I think that is why you have different plus and minus signs. I think it just depends on the signature and the convention that you're using. Okay, so let's have a 5-minute break. Can you tell us if the signature of the metric changes? No, the signature is stagnant throughout your computations. So you define a convention first and you do your computations. So if I define a convention where I'm using the signature to be, mostly plus, then I will use mostly plus signature throughout my computations. If I use mostly negative, mostly minus, then I will use that convention throughout my computation. So that signature does not change. It's just a convention that you use. Okay. So let's take a 5-minute break and I'll come back after the break at 44. Okay. Okay, let's start. We're kind of running out of time, so maybe I can just hurry up. Since the lecture notes are there, in case I miss anything, you can also study it from the lecture notes. They're pretty straightforward, so they should be pretty easy for you to understand. Okay, so where I was basically trying to understand how the components of a covector would transform, right? So we see that for a component as such, let's say x mu over here, it transforms with the Lorentz transformation as following, right? But what if I had an index that were downstairs? So in that case, I would have an inverse transformation, and you would have for a covector, which is like this, to transform with the inverse Lorentz transformation as follows. Okay, where this is basically the inverse of lambda mu nu. Okay, and obviously, we understand that this this is true because they would just have basically the reason why it transforms like this is you want the inner products of the covariant and contravariant components to be Lorentz invariant, right? Because they should give you scalars, and the scalars should be invariant under the Lorentz transformation. So for that to be intact, you would need the transformations to be in the following way. Okay. Now, of course, you can generalize these vector rules or vector transformation rules to tensors, right? In the way that we've seen earlier. And of course, if you have a tensor, T prime, that has indices mu1 up to, mu, let's write this as mu m. And let's say we nu 1 to nu m or n, like this. Then, of course, similarly, you would have equal amounts of the Lorentz transformation matrices as such, right? And of course, for the one indices that are, okay, maybe I should write the ones with downstairs. Then I can use the inverse ones for the ones that are downstairs, right? And I will have them up to as many of the indices I have, and it would act on the components of the tensor. As follows. So this is just a general extension to the vector transformation rule, which will follow in a similar way. So for the covariant components, you would have the lambdas, and for the contravariant components, you would have the lambdas, and for the covariant components, you would have the inverse lambdas. Okay, so similarly to special relativity and in general relativity, you would have tensors that you will use to formulate attributes of the space-time. And in fact, the most complicated tensors that you will encounter in special relativity is called the electromagnetic field strength, which is called F mu nu, which is an antisymmetric tensor, and also T mu nu, which is called the energy momentum tensor. Okay, and GR, the most complicated tensor that you will probably see is called the Riemann tensor, which is something that looks like this with 4 indices. Okay, now you might question why tensors are important. So the reason why tensors are important is because you see the tensors can absorb a lot of these properties, right? Transformation laws and whatnot. So using tensors, what you can do is if a physical law is written in one space-time, right, in a form of, let's say, tensors, that should be true in all reference frames. Meaning, if you have a tensor that is defined in one type of situation, even if that situation is transformed, Lorentz transformed particularly, it will still hold in that different reference frame. So that is very strong because that means that in any coordinate system or in any space-time that you have, if you define one tensor, it will be invariant in all transformed spacetimes and in all different coordinate systems, which is very important for us, because in GR we have these tensors and we have to deal with these tensors, and they must of course keep these attributes intact whenever we're dealing with coordinate changes and so on. Now, one of the most important symmetries of GR is called diffeomorphism invariance, which means that under coordinate changes, these tensors um, do not change their attributes. Okay. Now, this is also one of the reasons why, Newtonian mechanics does not actually sit well with SR or GR. Okay, that is because Newton's laws cannot be written in terms of tensors. However, Maxwell's equations can be written in terms of tensors, and hence Maxwell's equations will hold in all space-time frames. And they are also consistent with SR and GR. In fact, Einstein was actually motivated by Maxwell's equations because they did imply that, the speed of light is um, constant in all reference frames and also independent of the motion of the observer, right? Okay, so I don't really have much time, but I'll just go through this very quickly. So I'm skipping a lot of things that I think is trivial. Maybe you can read my lecture note and ask me questions later on if you have any. But I'll just go on to define the 4 velocity now from the 4 vector. So the 4 velocity is defined as u mu, which is defined as dx mu by d tau, where tau over here is called the proper time. And what I mean by proper time is basically it is the time that the particle basically experiences in its own reference frame. Okay, and this proper time is actually also Lorentz invariant. Okay, because all observers can agree on their own proper times. Okay, so that is also something that is Lorentz invariant, and that is what we're using to define the 4 velocity. And if you write the 4 velocity now in using, let's say, the differential of the proper time, which I have in my note, I will just refer to that. So the differential of the proper time is given as dt by gamma. And now if you use this over here, then you can write u mu as gamma acting on 1 and v, which you can see from here, because of course we know what gamma is, right? Gamma is just 1 minus v squared by c squared. And from here, if we write u mu, then this just means that I would have dx mu by this whole expression downstairs in the denominator. So I would have something like gamma dx mu dt. And x mu obviously has components x0, x1, x2, x3, something like this. So therefore, I would get for the 0th component, I would get gamma dx0, which is basically t. So dt by dt, which is 1. And hence I have a 1 over here. And the rest would just give me dx1 by dt, which is one of the velocities, so v1, right? And for 2, I would get dx2 by dt, which is v2, and so on. So for the rest, I would get some velocity. So maybe put a bar over here to define that this is actually v1, v2, v3 altogether. Okay? So therefore, you can define or basically write or rearrange the 4 velocity in this general form. And you can see also that in rest frame, u mu will take the form 1, 0, 0, and which makes sense, right? In the rest frame, you would have v to be, 0 because no velocity, and therefore those spatial components will just move. Now, another important thing that I can, of course, define is the 4 momentum, which is given as p mu, which is defined as m times the 4 velocity, u mu, where m is obviously the mass. And you can also use the definition of u mu from here and write p mu as gamma m 1v. Okay. And from this, basically, you can get a generalization of the 3 momentum which let me write it as P bar, which means that this is 3 momentum as in P1, P2, P3, as gamma mv, which is just for the spatial part, so taken from here. And the temporal part is actually the energy of the particle, where I only get gamma m for this part. Okay. Now, in the rest frame of this particle, you would get P mu, and this is also a very known result as MC000. Okay, you see that I reintroduced C over here, and for a trace or basically a contraction as such, I will get minus m square c square, because you see from here I can write P mu, and I can write this as eta mu nu P nu, right, for this part. And hence I will get eta mu nu P mu P nu, which will essentially give me the minus term, where you see that there is no minus term over here, but the eta essentially introduces a minus term in the temporal component. Hence, I will get minus m squared, or basically minus 1 for the eta, mc for the first, and of course plus da da da, but the others are 0 because all the others are 0 over here. Hence, I will only have this times twice of them because I have 2 of the p mu's, and hence I would just get m squared c squared. Okay. And since the inner product is obviously invariant, so this is a Lorentz scalar. So that means that it will take the same value in any frame. So it is invariant under Lorentz transformation. And also, if you don't want to use, let's say, the rest frame for momentum, but you want to use it for any particle arbitrarily, then P mu takes the form E by C Pi, where Pi is just the 3 momentum and E by C is the energy of the particle. And in that case, you will have P mu, P mu. You compute it in a similar way that I did over here as minus E squared by C squared plus P bar squared. P bar over here is just all the PIs altogether, okay? So from here, you can rearrange this equation and you can write E squared as P bar squared C squared plus M squared C to the power of 4. Because this M squared C to the power of 4 comes out from here, which we already computed via this equation. And also, since this is a Lorentz scalar, this will also be, valid even if it's not in the rest frame, right? So therefore, I can write P mu as minus M squared C squared. And since I have a C squared over here, and I am subjecting E squared over here, I can write rearranging this equation in this particular form, which is the famous generalization of the E equals to mc squared equation, except I'm including kinetic energy. Okay. Now, this is for massive particles, right? But what happens when we consider massless particles? Now, of course, I understand that when I have massless particles, they follow light-like trajectories. Basically, they follow trajectories that light take, right? Which means that ds squared equals to 0 for light-like separation, if you remember. And hence, the proper time actually breaks down, which is a problem in the analogy that we did. However, since we have E as this expression over here, so I can write E as P square C square plus M square C to the power of 4. But let's consider that C equals to 1 over here just for simplicity. So in that case, this will boil down to P square plus M squared. But for massless particles, this is still okay, right? And I don't really have any problem, as in I don't have any divergences or anything. So this just is P, okay? And hence, you can also define the form momentum for massless particles, and you would just get P. Let me write bar over here so that you understand what I'm talking about, with P mu equals to 0, which you can again calculate using the same method that I did earlier. Okay. So I know this was a run, but of course, special relativity is much, much larger than this, but I just tried to brush over the more fundamental things that we need to review special relativity. But yeah, this is all. There is one part in the lecture note that I don't have time to cover, but basically I derived Maxwell's equation in tensorial form. Maybe you can take a look. It's pretty straightforward. And, I have also denoted all necessary expansions. So in that case, if you have any question about that part, maybe reach out to me on Slack. But yeah, so this is it for the part of SR, and this officially concludes the preschool today. Okay, so there is a question: if an infinitesimal curvature is produced as a perturbation to Minkowski spacetime, how can we explain using tensor? Is it possible we neglect it? Oh, very good question, actually. If there is a perturbation to Minkowski space, so in general, sorry, in general, we have the metric eta mu nu to be the metric that is defining flat space, right? So if you think about this, this is actually just defining a particular manifold that has no curvature at all, right? However, if I introduce some perturbation, right? And by introducing perturbation, what I mean by that is, let's say I disturb the flatness of the background geometry. In that case, I have to add in a perturbation, which of course also has the same degrees of freedom, which means the same indices, right? This is actually called G mu nu. Okay, and G mu nu over here is actually the metric tensor component, which is valid for all non-trivial spacetimes, meaning G mu nu can actually also be boiled down to eta mu nu if you consider that the perturbation is 0. So G mu nu is the metric tensor component that works for all types of background geometry. Basically, of course, you have to define what G mu nu is for a particular space, but arbitrarily, G mu nu is a metric that should work for all non-trivial spacetime and also flat spacetime. Okay. Do you want to recommend some book for SR? Yes, there's a very good book by Taylor. I think his name is John Taylor. I'm not sure, but his last name is Taylor. And I think the book is called Classical Mechanics. And I don't exactly remember the title, but Classical Mechanics, just type in Classical Mechanics Taylor, you should get it. Okay, I think that's a very good book and something, a book that explains in a very nice language. So I would suggest this book for SR. Okay. Are there any other questions? I'm sorry, I might have gone over time today, but I had a lot of things to cover. John R. Taylor, yes, thank you. Thank you. Okay, so are there any other questions for me or for the upcoming lectures? If you have any logistical questions.
Should we turn off the recording?
Yeah, I think we're done.